Hello. Okay. Um, should see the desktop and you should be able to hear me by now. Does that seem okay? Let's see. Does everything seem okay? Can you hear me? You
Yes.
see? Oh, okay. All
Yeah,
right.
we can hear you and see the desktop. I
Okay.
can at least. Other
Good.
people are saying yes in chat.
Oh, I get it. I see it now. It took me a minute. For some reason, Zoom made me authenticate again. I haven't authenticated to Zoom for the whole semester, and all of a sudden, I had to go look up my Zoom password. Yeah, all of a sudden, it just said log in, and I hadn't done that for months. Okay. All right. What we're going to do today is start talk about linear transformations, which is one of the most important ideas in computer graphics. This is the way we really move things around. Okay. Now, let me download these two things. We've been moving objects in space naively by just doing what's kind of obvious, adding numbers to the coordinates. So you can move a vertex around in space by just adding numbers to its coordinates. Okay, and that seems like a pretty reasonable thing to do. Now, we never talked about, for example, rotating. We could rotate this way, but it's a little bit complicated. It's a little bit messy. But we can do anything we wanted to just by modifying the coordinates in a vertex. But there turns out to be a much better way to do this. Okay. Let me think of try to think of this is where I would really like to have a chalkboard. Um, Let me try using a yeah. So if we had a vertex V with stick to just two dimensions, like 3, 4. Okay. In general, if that's the x, y coordinates of a point, you can get a new. You can just you can just add to it. You can just take V plus 2, 3. Okay, that gives you a new vector that will give you 5, 7. So that just, that moves. You can think of, so V now, you can think of this as V equals V plus 2, 3. So you move V to somewhere else. Okay, so that's a real easy way to, now that's translating. Okay, what you're doing there is you just move. Well, that's not really, a point by itself, you can't say what you're doing. Am I rotating it or am I translating it? If I just talk about a point, it's hard to know really what I'm doing. Now, remember, our idea is if you have a square, you know, a square, our whole idea of what a square is it's really just those 4 vertices. If you think about, from our point of view, a square is something like this. So it's really a vertex 0, a vertex 1, a vertex 3, and a vertex 4. Okay, so our square for us is really 4 vertices. And everything in between, you get by interpolating between those 4 vertices. So if you want to move the square, you just have to move vertex 0, vertex 1, vertex 2, and vertex 3, and vertex 4. So that's what we've been doing. You change vertex 0, you change vertex 1, you change vertex 2, and you change vertex 3. Okay. If you modify those to be new vertices, you could rotate that. Depending if you use the right formulas, you can translate that, make it get bigger, make it get smaller, maybe even rotate it. Okay. Now we would do that by just updating one vertex at a time with the same set of formulas. Okay. Now what we want to do now is introduce the idea of a matrix. So a matrix, if we're in just 2 dimensions, a matrix is 4 numbers. Okay, a matrix is going to be an A, B, C, D. Okay, that's going to be a matrix for us. 4 numbers. Matrices are in row. They're like 2-dimensional arrays. They're in rows and columns. Okay, so there's a 2-dimensional matrix. It's got 4 numbers in it: A, B, C, and D. Okay, and you can take a matrix, and you can take the matrix and multiply it times a vector. Okay, and when you do matrix times vector, you write the vector as a column vector. Okay, so that's matrix times vector. So if I want, I can put the times symbol in between here. So it's matrix times vector. Okay, and the thing was, remember what you do is you go dot, you do a bunch of dot products. Okay, this row dotted with that column. You take that row dotted with that column. So the matrix times vector gives you vector. Okay, matrix times vector gives you vector. And in this case, the answer will be the vector. The first vector is AB dotted with XY. So it's A times X plus B times Y. Whoops, did it in the wrong place. Okay, so that'd be A times X. So that's this number times that number. And then I go across the row, then it'd be that number times that number. Okay, that's the first component of the product. Matrix times vector gives me vector. The second component of the product would be I go across this row and dot it with, again, this one column. So there's only one column over here. So I dot the row with the column. And that would give me C times X plus D times Y. Okay, so now what works great with this is to do this to M times V0. Do the matrix, if you have this geometric shape up here, do the matrix operation on each corner of it, on each vertex. So do this. Okay, do that. Yeah. Then we say you've moved this shape by the matrix. If you move every one of the corners, every vertex, if you just move the vertices in the shape by the matrix, you're essentially moving yeah. Now that's the alternative to going through there and just changing, essentially, well, actually, what I really should do is say that you get V naught equals matrix times V naught, then V1 equals. So I want to update it. Now, one of the things we'll have to talk about is how what we really mean by this. Okay, so I should think of it as I'm going to update the vertices. So the new vertex 0 is the matrix applied to the old vertex 0. The new vertex 1 is the matrix applied to the old vertex 1. So I get 4 new vertices. That would be this guy moved somewhere in space. Okay, all right. Now, here's a reason why this is so useful. Okay. One thing I would do is I would write a for loop to that. So I would say, if this guy here is a model, so this is a model. So think of it as a model object. Okay. I can say for vertex V in the model, now let's see. What I want to do is something like this. This is not going to really be correct Java, but I'm going to say okay, let me use the for loop version. for int I equals 0, I less than the model dot vertex list dot length plus plus I. Okay, so for now I'm going to walk the list of vertices 0, 1. Oh, I wrote these wrong. 0, 1, 2, 3. Okay, I'm going to walk the list of vertices, and I'm going to say, vertex list dot get I, or I'm sorry, vertex list dot set the ith element in the vertex list to be the matrix times the vertex list dot get the ith element in the vertex list. Okay, now it looks a little bit messy. That's this. Okay, I'm going to go through the vertex list, v0, v1, v2, v3. So for every I, starting at the beginning up to the length of the vertex list, then what do I want to do? I want to set the ith element. So vertex list dot set. So I'm going to replace, in the list, I'm going to replace the 0th element with this. I'm going to replace the first element with this. I'm going to replace the third element with this. So I set the ith element to be the matrix times, then I get the ith element. So I get the ith element, multiply times the matrix, and set that as the new ith element. Okay, so notice that that's not this. That's not really doing this. This is not doing this. Does anybody see why? There's a subtlety here. Why is this not doing this? One of the things we're going to be talking about is object-oriented programming and kind of getting used to what object-oriented programming really means. Okay, I'm setting the ith element in the vertex list to be m times the ith element in the vertex list. So it looks like I'm saying, okay, the 0th element in the vertex, okay, but it's not this. It mimics this, but it's not. So let me see what's different between this and this.
Is it actually multiplying each element in the in each vertex?
Yeah. Oh, yeah. This here means what I wrote up here.
Okay.
Yeah, it means the matrix times the vector. Okay, so matrix times vector or vertex, matrix times vertex. So this thing is this right-hand side here. That's not the problem. So that means all these right-hand side. So each of these right-hand sides is that. Okay, so that right there is that right-hand side. Okay, what's the difference between this and this?
Is it creating a new object?
Yeah, and doing what with it?
Adding it to the vertex list along with the old one? I mean, the old ones are
Well,
there,
what
right?
happens to the old one?
It
When you
doesn't
set
get
the ith component to be a new object, what happens to the old object at the ith location?
Hmm.
Okay, so this creates a new object. It creates this right-hand side object. Okay.
Does it replace it?
Yeah. Well, yeah. So what happens to the old one? See if I can draw a picture to it.
They're saying in chat the garbage collector destroys it.
Okay. Yeah. Why? Okay. Here's a picture of a list. Okay. Actually, let me do it differently. If I have a list object, here's a list object. Okay. That's a list object because that's what we're dealing with. We're dealing with over here with a list of vertices. Okay. Now, what does the list object hold? What's in here? This, oh, I should have put, this is a list of we can be more precise. This is a list of vertex. That's what yeah, it's a list of vertex. What's in here?
Pointers?
Two
Vertex objects?
for vertex objects. Okay, so so inside here are a bunch of references. There's a bunch of references. They're reference variables. Okay. Now, what do? They point at vertex objects. So there's a vertex object, another vertex object, another vertex object. Okay. So there's a bunch of vertex objects. Okay. So I would label, so this is a vertex object, a vertex object. Kind of tedious to draw these out, but it's kind of useful because you should it's really important to be able to draw these pictures for any kind of situation in object-oriented programming. It doesn't even matter if it's C, C++, or Java. If you can draw these pictures, it helps a lot. Okay, then what happens? This guy holds this one holds a reference to one of the objects. This one will hold a reference to another object. This one holds a reference to another one of the objects. Okay. This one holds a reference to another one of the objects. Okay. So, and then I can put indices on here. Like, you know, this would be at index, say, 0. This one's index 1. This one's index 2. This one's index 3. Oops, there's index 3 and index 4. Okay, so that's these guys. You know, set I or get I. That's the I. So there's the 0, 1, 2, 3, 4. Okay. So there's four. Let's see. Oh, and then I don't have two. I should create another vertex object. You can't actually have an empty slot, so I should have a vertex object for 2 to point to. Okay. And that's another vertex object. Okay. Now what's going to happen when you do this loop here? Okay. Now, what does this seem? Think about that line there. So vertex 0 is this one here. Okay. When you see that, what do you think? And there's no real right answer here, but just like, what do you think is happening to this vertex object? You know, inside here, there's an X, a Y, and a, well, I will just keep it two-dimensional. There's an X and a Y coordinate in there. Okay. When you see something like this, which does this, what does that kind of make you think in this picture here?
Makes you think that the new value is just being stored right back in the same place.
Yeah, it kind of makes you think that you're letting V0 get new values for its X coordinate and Y coordinate, right? What's the fancy word for that?
Mutability.
Yeah, you would think that you're mutating this vertex, that this X gets replaced by that, and this Y gets replaced by that. Okay? You could be, now that's what we're doing. That's what we've been doing in our renderers, our app, in your homework assignments. That's what you've been doing. You have been going to this vertex and replacing the numbers inside of it, then going to this vertex and replacing the numbers inside of it, then going to this vertex and replacing the numbers inside of it. Okay, you've been mutating the vertices. But what does this, so that's what this thing seems to imply. Okay. Now, actually, that's actually not what it says either. Okay. This is actually this is a standard idea in mathematics, but in Java programming, if you think about it, this is very ambiguous thing. Okay. So for example, you might think it means change what's in that vertex, update it. But on the other hand, this could be what? Well, if this was Java and I have a name like V0, what am I supposed to think? Is it right to say V0 is a vertex?
It could be a different vertex object than the one on the right side.
Okay, well, first of all, is it correct to say that V0 is a vertex? That's a tricky question. There's multiple answers to it. Is it correct to say that V0 is a vertex?
They said in the chat it could be it's a pointer to a vertex.
Well, we don't use the word pointer in Java. No, what is it? In Java, it is
A reference variable.
A reference variable of type
Vertex.
vertex. So if somebody asks you, is this a vertex? You gotta go, well, yeah, kinda, because what are the two things that have type vertex? Java, Java, Java.
A
What's
child class can have.
No.
No?
Look at that line of code. I just typed a line of code. What to do?
Instantiates new vertex object and says point it to the reference variable V.
Well, you said you had all the right words in the wrong orders. Yeah, you had the right words. All the right words were there, but you said them in the wrong order. Okay, what does that line of code do? Real important. What is that line of code? Creates a vertex object. Okay, that's where. That's this. Creates a vertex object. Notice that it's an object of type vertex. So there's one thing that has type vertex. Then what else does it do? And
Reference variable of type vertex?
yes, a reference variable type vertex. That's a second thing in the Java language that has type vertex. Those are two different kinds of things. This thing is a reference variable of type vertex. This thing is an object of type vertex. And then what does this thing do? The equal sign.
Assigns the address to the reference variable?
Well, there is no address. Stop thinking this is C++. It is not C++. This guy does not have an address. It's Java. Java language does not have addresses. It does not have pointers. It does not have addresses. If this was C++, that would be a reasonable thing to say. Java has what we call opaque pointers. You don't know what they are. If you think they're addresses, one day you'll find out you were very wrong. Or you might, it might be that in some Java virtual machine out there, the opaque references actually are addresses. But most of them that I know of, they're not. They're not implemented as addresses. They're usually implemented as hashes into a hash table, something like that. They're usually like hashes into a hash table of references. Okay, so this guy is an object in the heap. This guy is a reference variable, usually in the stack, but it doesn't have to be in the stack, but it's a reference variable. And this makes the reference variable refer to the object. We usually draw it as an arrow. we think of it as the reference variable pointing at the object, but you have to be really careful. It's not a pointer because it's not an address like it would be in C++. In C++, you take the address of this object and put it in that variable. Okay. Actually, that's only true even in old C++. In modern C++, even that's not even true in modern C++ when you start getting things like smart pointers. Things get much more complicated. Okay. So, but that's an object of type vertex. That's a reference variable of type vertex. Okay. Now you go back over to here and you start thinking, well, okay, what could this thing be doing? We said, one thing we said was, yeah, it just updates the values in here. Okay. It creates new values and puts them in here. But what else could it do? Instead of putting new values into this thing here, what else could this line of code be doing? If you draw a picture, here's the reference variable called V, and that's a reference variable of type vertex. And over here is an object. Let's see. Over here is here's an object of type vertex. Okay, and it's got an X and a Y in it. Okay, and we assume that this thing points to that guy. Okay, and then we also have we got another reference variable of type matrix. It's called M. And over here, there'd be a matrix object. There's a matrix object over here. And, we'll assume the matrix has 4 numbers in it. A, B, C, and D. Okay. And the matrix object points to here. Okay. And somehow you're going to multiply this matrix times that vertex. Okay. You're going to do this right-hand side. Okay. What can this equal do? Now, this is not Java. Right now, this is not Java. But think of it. You're going to take this stuff here, and you're going to do this mathematical operation over here. Okay. And then this represents something that you're going to do. Okay. Think of it. What can I do over here? I've got this reference variable pointing at that vertex object, this reference variable pointing at that matrix object. There's 2 numbers in here, 4 numbers in here, and now I want to somehow do this thing. What are the possibilities over here?
Do you create a new vertex with the?
Yeah, one possibility is we create a whole new vertex object. And inside of it would be AX plus BY and CX plus DY. Okay, now suppose so that would be this right-hand side. But then what do I do to finish this equation?
You either reassign the reference to V0 or create a new V0, then assign the reference.
Well, no, I'm saying do this. So if I'm doing that formula, what would I now do?
Oh, you're replacing the value in the old vertex with the value from the new vertex.
No, but that doesn't make sense. Well, we said that we create a new vertex object. And I said, okay, so this right-hand side created a new vertex object. Okay, that's fine. But then how do I finish this?
Replace the reference of V0.
Yes, replace this reference so that now instead of pointing at, you would essentially replace this reference, replace this one with a reference to there. Okay. What happens to this guy now?
It's lost in the memory and get deleted.
Pardon me?
Get deleted.
It'll be garbage collected because it'll no longer have a reference to it. Okay, so that's one thing I could do. This equation in math could mean that the right-hand side creates a new vertex object with the data in it, and then I update the reference on the left-hand side to point at the new object. That's one possibility. Now, what's another possibility for this guy?
Mutate the original vertex value.
Yeah, just take these numbers and put them in here. Just update this vertex value, this vertex object. Go ahead and do this equation by updating this vertex object and not create a new vertex object. Okay? Those are two fundamentally different things in Java. When you want to implement this guy, you have two fundamental choices of design. Now the language doesn't care a whit which way you do it. The Java language can do it either way. You have to decide how you're going to do it. When you want to say that I'm going to take a vertex and multiply it by a matrix, do you want to say that that creates a new vertex object that you can then assign the old vertex reference variable to? Or do you want to mutate the vertex object that you're multiplying? Do you want to essentially modify this guy, okay, in place? Now, Java will let you do it either way, okay? Now, go back to this loop here. What is this loop doing?
It's creating a new vertex and replacing the reference.
Yeah, so it's going to replace every one of these vertices with another vertex. So what it's going to do is, as it walks this list, 0, 1, 2, 3, 4, every time it lands on a vertex, every time it gets a vertex, it'll create a new vertex. It'll create a new vertex. There's a new vertex with the AX within it will be AX plus BY and cx plus dy. Okay, it creates that new vertex. That's vertex, that's this thing here, m times the old vertex. So that's m times this vertex creates this new vertex. But then you set I to that new vertex. So that means you'll then change that pointer. Whoops. You'll change that pointer, change that reference to refer to the new vertex. So you'll update the reference. So this creates the new object, but then this sets the reference variable at that location to the new object. Then this one will probably get garbage collected, unless there happens to be some other arrow pointing at it. Then you walk to the next item in the list. Then you get to this item in the list. You will, the right-hand side, this right-hand side will create, it'll take this vertex, apply the matrix to it, which will create a new vertex. So in here was, this one had its own x and y value. It'll create a vertex here with ax plus by, ax plus by, and then that'll be this. Okay, matrix times that vertex will produce this new vertex, and then you'll set the ith pointer. We're now at I equal 1. We'll set that pointer, that reference. We'll set that reference instead of referring to this guy. Oops. We'll update that reference instead of referring to that guy. We'll redirect that reference to point to refer to that guy. Oh, no, sorry. Refer to that guy. Okay. And then you walk down this whole list, and this vertex will be used to create a new vertex. Then the reference from this vertex will refer to the new vertex. This one will probably get garbage collected. Then this vertex will be used. You use if you look at this formula, you're using the current vertex. You're multiplying the matrix times the current vertex to create a new vertex. And then you're setting the reference variable to point to the new vertex. Okay. So now that's, now this, the way I wrote it here pretty much means you have to do it that way. Now, remember we said over here that you could either make this, you could either mutate this guy or point it at this other guy. So you can either create a new vertex and point this thing at this one, or you could mutate this vertex. So this thing mathematically can either mutate V0 or replace the reference in V0. Okay, now this is really kind of weird. When I say mutate V0, that doesn't make sense. It should mutate the object referred to by, notice I have to say it in a real awkward way. Mutate the object referred to by V0. So that means V0 points to some object, and you use the matrix to mutate that object, or replace the reference in V0 to a new object. Okay, that's in words the two strategies. Okay, mutate the object referred to by V0, or replace the object I can summarize it by saying by mutate the object referred to by V0 or replace the object referred to by V0. So there's a slightly more precise way to say it. Either mutate the object referred to by V0 or replace the object referred to by V0. Okay, either mutate this one or replace this reference to a different object. Okay, this mathematically doesn't say what to do program-wise. Okay, this is just saying, this is just somehow saying that I want a new vertex that's m times the old vertex. This mathematically, this would seem to imply you're mutating the vertex, but that doesn't, it doesn't have to be that way. This down here doesn't mutate, it replaces. Okay. Now, this one does the replacement. If you want to do the mutate, you'd have to write the code a little bit different. Here's how it might look like if you were going to do mutation. Okay, so this is the code for replacing. So that's the replace one. Now, the mutate one would have to look like this, something like this. You'd have to get the vertex at I. Okay. So you get a reference to this vertex. And then on that vertex, you'd call the times method with a reference to m. And that would say, to go to the vertex list, get me a reference to that vertex. So go to the vertex list and get me a reference to that vertex. Well, go to the vertex list and get me a reference to that vertex. Then call the times method on that vertex using the matrix M and update that vertex. Okay, so that would be what the code would probably look like if you wanted to mutate the vertex, because then you have to say, call this method on that vertex because it needs to update that vertex. So you'd have to call the method on the vertex. Notice that this puts the things kind of awkward. That makes it look like here, see, the matrix is multiplied with the vertex. That's what it says over here. This is written really weird. You have to take the vertex and think of the vertex as being multiplied by the matrix. It kind of switches things around. You start with the vertex and say, okay, vertex, here's a matrix to multiply yourself with. Okay, so you're saying, here, vertex, be helpful and multiply yourself by this matrix. Okay, that would then modify what's inside the vertex. Okay, so the code would look a lot different. So this would be mutating, replacing the vertex, or mutating the vertex. Very different code. Java doesn't really care which one you do. Modern programming practices tend to favor replacing over mutating. But mutating can be much more, depending on how you write the code, sometimes mutating is faster. Okay, and so you might quibble over this. Like, you might claim that you can write faster code if you mutate. Why, does anybody see why it might be faster to mutate? Think of like over here.
Less steps.
Why?
Because
there's one big step saved, right? You're right, less steps. And what's the big step that you save if you do mutating instead of replacing?
Reassign reference.
No.
And creating a new vertex.
Creating a new object. You save creating an object, which is an expensive operation. See, mutating would just update those variables. It wouldn't update the reference. It wouldn't update this. It wouldn't cause a garbage collection. So you notice that the replacing causes you to need to create a new reference object, a new object in the heap, and you'll also cause some object to get garbage collected. See over here, you had to create this new object, and then you'll have to garbage collect this old object. You have to create this and garbage collect that, as opposed to just updating this one with a couple new numbers. Okay, so you can make a strong case that this is faster. Okay, now the Java virtual machine goes through massive amounts of effort to try to make this almost as fast as this. That's actually one of the huge design goals of the modern Java virtual machine, is to make this idea that you would create a new object, update it, and then change the reference to that object and garbage collect these almost as fast as updating this. Okay. Now, this is much easier to analyze. This code is less buggy. Mutating tends to lead towards somewhat buggy, hard to follow code. So it may be faster, but it also tends to be a little harder to maintain. This tends to be a little bit easier to understand and maintain, but it might be slower. But the modern Java virtual machine has gone through huge effort to try to make this strategy as fast as this strategy here. Okay, so modern Java programming favors this.
I have a quick question.
Yeah.
So I'm thinking back, and don't we call getters accessors and setters mutators? And so then how come a setter isn't mutating, but an accessor is?
No, the only mutator is the setter. The getters are not mutating. Their accessors do not mutate.
Right.
Accessors are fine. It's the setters that cause problems.
Right. So, so I'm just mincing words, I guess. So how come we're actually mutating with the getter, but we aren't with the set? We're replacing, but we're not mutating. So why do they call setters mutators then?
They are. Who am I mutating?
Well,
You're mutating the reference.
Yes.
Who am I mutating there?
Just the reference.
What object is being mutated by that set? That set method mutates something. Sets mutate.
It's the vector object.
No.
No.
Well, there is no. I don't know what you mean by vector. I don't have anything up there called vector.
Oh, vertex.
No, it's not mutating the vertex. No.
Okay, that's what I didn't think it was. That's why I got confused. It's just changing the point, the reference.
So who is it mutating?
Okay, so just the reference then.
No, that's not the
vertex list?
object. References are an object. What object is being mutated by that word set?
Is it the vertex list?
The list object.
Okay.
See,
Got
it's mutating. See, it's mutating. See, look, it sets those references. It mutates something in the list object. There's a field in the list, and it's mutating it. So this mutates the list object. Okay. That's different than mutating the vertex object. This, where did I write it over here? This does what? Go to the vertex list,
Right.
get a reference to the ith vertex, then do what to that vertex object?
The vertex object times the matrix.
Yeah, so what am I doing? Am I mutating someone?
You're mutating the vertex object.
Yes, this mutates the vertex object. There's the mutation. This one mutates the list object. Now here, what's this do? Think about that versus this. This one took M and used it to mutate the vertex object. This one does what?
Create a new vertex.
Yeah, this will take the data in M and the data in that vertex and use them to build a new vertex object. So it's not mutating anybody. It doesn't mutate him. It doesn't mutate him. It can't mutate him because you can't mutate someone you have a reference to. But it does not mutate the matrix. It uses the matrix to create a new vertex object. So it'll create a new vertex object. Okay, and then that new vertex object, that's this guy here, that new vertex object is then put into the vertex list. So you mutate the vertex list. Okay.
So the times function in the matrix and the times function in the vertex is not the same.
Of course not. Yeah.
Okay.
Yeah. Now they kind of, well, see, the word the same is a very fuzzy word. Okay. You answer, are they the same? There's a times method in here and a times method in here. Are they the same?
They have the same process, but it returns different things.
Right, yeah. They both do these sets of formulas, right? They both do those formulas. But one does it from the point of view of building a new object, and the other one does it from the point of view of mutating a current object. So they both do the same thing. They apply those formulas, but they don't do the same thing. This one builds a new object, and this one mutates an object. So the answer, do they do the same thing, is yes and no. They both implement the matrix multiplication formula, but one creates a new object and one mutates a current object. This one is in the matrix class, and its job is to say, take this matrix, take this vertex, and build a new vertex that is the result of applying that matrix to that vertex. This times is in the vertex object, and its job is to take this matrix and use it to mutate this vertex object. Both times using these formulas. Okay. Now, part of what we're doing is saying that you really now have to start understanding object-oriented programming. Because what we're doing is we're saying all the different ways that you can take the tools of object-oriented programming and start implementing real-world situations, like implementing mathematics. And we see that there's a lot of ways of implementing real-world things with object-oriented programming. If you go to the folder for render 7, see this folder here, object-oriented matrix operations? It's all about these different ideas. And we're going to talk about these. We'll go through the details. I actually implemented these different strategies. What are the two different strategies? The strategy that this thing mutates V0 versus this thing creates a new V0 and then mutates this reference variable. Okay, those strategies are actually implemented in various different ways down here. And then you could run these programs and just kind of look at the differences. It's a little bit messy. It takes a little bit of reading. But for example, here's a matrix class. So I implemented a matrix class, and then I do some various matrix times vectors up here. Well, actually, here I'm actually just doing matrix times matrix. I'm actually not doing matrix times vector. We're going to also talk about what it means to do matrix times matrix. So these mostly do matrix times matrix, but there's still the same idea of the difference between mutating and not mutating. Okay, so there's that. There's a whole folder of things about that. And then there's a file down here, kind of summarizes what we've been doing here. Okay, like, what does that mean? What this is supposed to mean is matrix times vertex. We haven't talked about matrix multiplication, but this is matrix times vertex. And it turns out there's a whole lot of ways of doing it. Okay, and we're going to talk about these different object-oriented ways of thinking about this stuff. Okay, so these pictures we've been drawing, we're going to keep coming back to them, and now the renderer does things one way. The renderer does things even though I say there's more than one way to do things, the renderer pretty much does things one way, which is the way I think is probably the better way. Though people can argue. People always argue about design. Some people think one way is better. Some people think another way is better. Okay, so the renderer will do things one way, but it's worth thinking about the possible ways that it could be done. Okay, all right. So now, here are the two ways to think about this. That you're gonna, we're back to what we're talking about is we've got a model object. So there's the model, and we want to move it. Okay, the model object is made of these vertices. Okay, and what we want to do is use this matrix to move the model. And this is our idea, is that we apply the matrix to each vertex instead of just updating the vertices in instead of updating the coordinates of the vertices directly like we've been doing, we want to use a matrix to do that. We want to use a matrix to update the vertices, not what we were doing before. Okay, so we want to put this in a uniform idea that we use a matrix instead of just going in, grabbing the vertex coordinates and doing something to them. We want to always multiply vertices by a matrix. But these formulas don't really have, they're not programming. This is not code. Those formulas can get translated a couple different ways into code. You know, this replacing way or this mutating way. Okay? All right. Now, why do we want to use matrices? Okay. The reason we want to use matrices is the following. Suppose I want to move this matrix, this object a couple times. Suppose I want to do something like, I want to take my model, translate it, then I want to rotate it, then maybe I want to scale it, and then maybe I want to do something else to it, maybe translate it, maybe translate it again. Okay. Right. So what if I want to take a model and do several operations to it, one after the other? Okay. What we're going to do is each one of these is going to be a matrix. That's matrix 1. That's for the translation. Matrix 2 will be the rotation. Matrix 3 will be the scale. And matrix 4 will be the translate. Okay. Okay. So then I would say something like this. 4 So for every vertex, okay, what am I going to do? Well, first I need to take the vertex and translate it. So I'll do something like this. I'll say vertex V2. Let's see. What's a better way to think about this? Let me just use the mutating one. Okay. So let me just think about it from this point of view. Okay. So I'll mutate the vertex with M1. Then I'll mutate the vertex again with M2. Then I'll mutate the vertex again with M3. And then I'll mutate the vertex again, whoops, with M4, okay? Okay, that will give me these transformations. I'll move the object, then I'll move the object again, then I'll move the object again, okay? Okay, all right, so that would be translate it, rotate it, scale it, translate it, okay? Mutate, 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 okay? Now, if I think of this in terms of a formula, I'm writing something like this. For each vertex I, it's going to be M4 of M3 of M2 of M1 of the vertex I. Okay? See, you take the vertex I and you multiply it by M1. Then you take that guy and multiply it by M2. You take that guy and multiply it by M3. You take that guy and multiply it by M4, and that's your final answer. Okay? So that's, notice that reading from top to bottom here was reading from inside out here. First, the vertex was multiplied by M1, and the results stored in the vertex, so it gets mutated. Then that mutated vertex gets mutated again by M2 and gets put into the vertex. Then it's mutated again by M3, put back in the vertex, mutated again by M4, put back in the vertex. Okay. Now, let's see. Now I don't really need the parentheses in here. So let me write this a slightly different way. So this is M1 times MVI. Well, actually, I should put the parentheses. So M1 times VI, then M2 times that. Okay, there's a new vertex. Then M3 times that, and then M4 times that. Okay, so there's a little bit cleaned up. I'm working from inside out. Okay. If you go back to linear algebra, one of the rules you learned was that matrix multiplication is associative. So the above formula is the same thing as this. I can regroup this formula. Instead of saying matrix times vector gives me a vector, matrix times vector gives me a vector, matrix times vector gives me a vector, matrix times vector gives me a vector. It's a lot easier to say matrix times matrix times matrix times matrix. That gives me a matrix, matrix times vector. Okay. Now, why would I do this? This code can now be abbreviated to the following. Did we see what's the advantage?
Are you saving the matrix multiplication, only having to do it one time?
Yeah. Well, yeah. Look, yeah. You're only doing this matrix. Well, you do this matrix multiplication. First of all, this list could be in the thousands or hundreds of thousands, even millions long, right? So if this list has length, say, 1,000,000, you're doing this, you're doing all this 1,000,000 times, okay? Now, that means that this matrix times this matrix times this matrix times this matrix is done 1,000,000 times, because first you have to do this matrix times this vertex, then this matrix times that vertex, then this matrix times that vertex. So you're multiplying these matrices 1,000,000 times. Here, how many times do you do the matrix multiplications? There's 1, 2, 3 matrix multiplications there, right? And then there's how many matrix multiplications in this loop? Suppose the length is 1,000,000. Okay, suppose the length is 1,000,000. How many matrix multiplications does this loop do?
4 million.
4,000,000. Suppose this length is 1,000,000. So this length here is 1,000,000. How many matrix multiplications does this loop do?
1 million.
1,000,004.
30.
1,000,004 or 1,000,003. Yeah. This does 4,000,000 matrix multiplications, 4,000,000 of them, because for every loop, there's 1, 2, 3, 4 multiplications. This one does 3 of them up here, but now this guy's pre-computed. Then it needs to do 1,000,000 of them down here. So the total is just 1,000,004 matrix multiplications versus over here, (1,000,004) matrix multiplies versus over here, it was 4,000,000 matrix multiplies. this is why we use matrices. This is actually why. I mean, well, this is probably the main reason. They actually are they make a lot of things easier, but they also make things way more efficient. If you need, in the way we've been doing things, if we wanted to do this, a translation followed by a rotation, followed by a scale, followed by translation, we would have to have done it this way. But instead of using matrix, we would just go in there and mutate that vertex to do the translation, mutate that vertex to do the rotation, mutate that vertex to do the scale, then mutate that vertex to do the translation. That's how you did the previous homework assignments. Every time you needed to move a vertex, you had to go in and update the coordinates inside the vertex. So and that works. I mean, in the old days, renderers were written that way. And before they thought of this idea of matrix multiply, that's pretty much what they did. You would just reach inside the vertex and change the numbers in it. Okay. Then somebody had the idea that this thing should be done with matrices because of this idea here, that if you're going to do a bunch of transformations in succession, you can pre-multiply the matrices. And once you've pre-multiplied the matrices, then you hit all the vertices once with the pre-multiplied matrix, which includes all these transformations, and you get a massive savings in efficiency. Okay, all right. So this is a huge gain, and it really is because of, well, it's because of how often you do this kind of a thing where you translate, rotate, scale, translate. You do a bunch of successions of transformations, one after the other. So you're going to do a bunch of succeeding transformations, but here you can that little guy there. So this is the rule that says that matrix multiplication is associative. Okay, now that means that you can change the order of the parentheses. You're not changing the order of the multiplies. You're changing the order of the parentheses. Instead of doing that multiply first, followed by that multiply, followed by that multiply, followed by that multiply, you're doing these 3 multiplies first. And then after you do those 3 multiplies, then you do this matrix vector multiply just once. Okay, notice that this is 1, 2, 3, 4 matrix vector multiplies. This is 1, 2, 3 matrix multiplies and 1 matrix vector multiply. So there's 4 multiplies up here and there's 4 multiplies down here. But once this guy's been pre-computed, then in a loop, you only do it one time. You'd have to be really dumb. A novice programmer would make the following mistake. See, a novice programmer would make that mistake. Move that guy inside there and go, well, let's see. If it's okay to do this, then I'll create this matrix here, and then I'll multiply it times the vertex, and I'll loop through here. Okay. Yeah, and then you're losing all the efficiency because then you're going to do this thing every time through the loop. Okay. Suppose you really wrote that code. Suppose you wrote this. Does anybody have a sense what might happen? Would it really hurt you to write the code that way?
It will have the same result. Just takes longer to run.
Would it be? Would it be? Would it take longer? Modern compilers are amazingly smart.
Oh, it automatically puts it outside.
Yeah, that's called a common fact. It can factor out it. The compiler, if it's a really good compiler, it'll see that line of code, the line of code that I've labeled 59, is what?
It is the same throughout the loop.
Yes, it's independent of the loop counter, and the compiler will lift it out of the loop. They'll factor it out of the loop. So if you actually wrote it dumbly like this, a modern compiler would say that line of code doesn't depend on I, so it's the same every time through the loop. So it'll lift it out of the loop, and then it'll end up writing it the original way. It'll write it this way. It'll do it for you. But that depends on, now that means you have to turn on the optimizations in the compiler, and it has to be a good compiler. But truth is, if you did write it this way, with most modern compilers, it would still end up being okay. The modern compiler would lift this out of the loop for you because there's no mention of I in here. The compiler would notice that. If there's no mention of I, it's doing the same calculation every time. Okay, so you know, but that's the key. This idea here, a bunch of transformations in a row being rewritten this way, so that my loop can go from this loop to this loop. That's one of the key reasons why we use matrices. We gain a huge efficiency with them. Okay. Now let's see. Now, there's several things we still need to talk. There's a bunch of things we still need to talk about. We need to actually implement matrix multiply, and we need to actually implement vertex matrix multiply. Okay, and we have to talk about our design choices. Are we going to do mutation, or are we going to do creating new objects? I mean, are we going to do things this mutating way, or I'm sorry, are we going to do things this mutating way, or are we going to do things this replacing way? We've got to make choices about that. Okay, and then so that's going to be, we're going to look at the code. We'll talk about the code for either one of these possibilities. The renderer actually uses this one. The renderer does things this way. So we'll look at the code. I'll show you the code that what it would look like if you did it this way, because some people might think that that was better. So you can write it either way. And then the other thing we need to look at is, well, what does the matrix actually look like for translate, rotate, scale? Okay, we need to know what the matrix for translate looks like, what the matrix for rotate looks like, and the matrix for scale. And those are actually the only three operations we need. We need to be able to take objects and rotate them, translate them, and scale them. Turns out that in computer graphics, that's pretty much 99% of what you need to do. Rotate, scale, and translate. So we need to know what the matrix looks like for this, this, and this. And if you look in that folder called rendering, if there's a folder here on transformations, there's what the matrices look like. Okay, so we're gonna talk about what these matrices here. These are the matrices. So there's scaling, translation, we don't need reflection, but this one actually shows reflection, and then rotation. And there's rotation around the x-axis, y-axis, and z-axis. So there's three different rotations. Actually, there's a lot more than three rotations, but we're just going to use these three: round x, round y, and round z. Okay. So there's pictures to show you and then here's what they look like in 2 dimensions. In fact, the 3-dimensional ones really are these 2-dimensional ones with just an extra row added to them. So one of the things we need to do is learn the matrices for translation, rotation, scale, and then look at how to actually implement things like matrix times vertex, or matrix times vertex this way. You know, matrix times vertex these 2 different ways. Okay? All right. Okay, so that's an introduction to matrices. Oh, actually, there's another thing we have to. I haven't reminded you of how to do matrix multiply. We did matrix times vertex multiply, but I haven't actually said. I'll remind you after Thanksgiving. Remind you, what does it mean to take matrix times matrix? You might want to look in your linear algebra book, or the references talk about this too. But we need to remember what it means to matrix times vector and matrix times matrix. Okay, because we're going to use 2 kinds of multiply. Notice that we use the same symbol here, but like here, it's matrix times vector. Here, it's matrix times matrix. Okay, so this symbol is overloaded. That multiply symbol is overloaded. This is matrix times vector. This is matrix times matrix. So we have to remember what matrix times matrix looks like. So those are the things we still have to talk about: matrix times vector, how to implement them, how to write a matrix for translate, how to write a matrix for rotate and scale. And then the last thing is how to use this to make our renderers work better. how can you use this stuff to make graphics better? Okay. All right. So that's what we'll be working on when we come back from Thanksgiving. There's still a lot to talk about with matrices. It's a big topic. It's a really big topic. Okay. All right. So we'll go ahead and quit here. We'll go ahead and quit here. And remember, this week is Thanksgiving break, so we'll meet again a week from today. Okay. And if you have any questions in the meantime, if you have any, play around with this render 7. Yeah, it's kind of, the main thing the render lets you do is now rotate things. Okay. So you have the ability to rotate. Okay. So that's from the point of view of playing around with the code. The one main thing that you can do now that we couldn't do before is rotate objects. Other than that, it would seem that there's nothing much really new in this render, even though this render is a huge jump from the previous render. Putting in the matrices is a big, big step, but it only appears as if the only thing you were gaining is rotation. Okay, so I'll go ahead and quit. Where's my quit button? Okay, all right, so have a nice Thanksgiving. Let's see. Did I turn off sharing already? Okay, so have a nice Thanksgiving, and we'll meet again a week from today. Bye-bye.